So welcome to another of our ASEG webinar series. This one is hosted by Western Australia, and I'm the local Western Australian ASEG President, Todd Majeski. The talk today is by Rich Bartlett, and his talk is entitled Pre-Stack Depth Imaging, Challenges in Exploration Scale Volcanic Geobody Model Building in the Potiguar Basin, Brazil. Now, before we can get to that though, I've got to go through some pretty much quite a few slides to get through here to let us know what's going on. So firstly, I'd like to thank our corporate members. Without them, we couldn't be doing this webinar, and we wouldn't be doing a lot of different things across Australia. So in particular, I'd like to thank the Corporate Plus members, High Size, Total Seismic, and Bell Size, and also the corporate members, Southern Geoscience, Transparent Earth, Santos, and Doug. And without them, we'd be a very small group of people. But also we've got a lot of brand sponsors. We've got, you can see how many we have in WA. I'd like to thank everyone personally, but we don't have time. SA and NT also have one heck of a lot of sponsors, and New South Wales also. Thanks to all of them. And they are helping us go through a lot of our activities. Zoom etiquette. There's a good slide for this. We won't allow people to just interrupt and ask questions verbally, but you can just go down below, find the Q&A button, and type in your questions. At the end of the talk, we'll go ahead and answer each and every one. And speaking of webinars, there are a couple upcoming webinars. First is tomorrow, and it's a continuation on a workshop that is pretty good, and this one's quieten your inner critic. And so I invite people to, if you haven't applied, go ahead and register for that one. It's free for ASEG members, only 25 for outsiders, and we still have time. Next week, in 1 week, we'll see that we've got some student talks from Macquarie University and University of New South Wales. And that one should be pretty interesting. Those are always fun. Now, it's not just webinars that ASEG is good for, of course. We have our own technical journal, Exploration Geophysics, where we get to read about some really high quality research results and case studies, not just from Australia, but from around the world. And of course, we also have our own chat mag, the preview, where we can see what the current trends are. And that one is a bi-monthly magazine, and it's now working well now that it's adapted to the COVID kind of problems. So you should be getting those in the mail pretty much regularly now. Yes, we have reduced entry to the AGC conferences, and of course free entry to any of the local regular technical events in your own state. Those might be a bit on the sparse side because of the coronavirus, but they're starting to open up again. And access to job advertisements, yes, very important nowadays. And hopefully some of you have taken advantage of the annual wine off, but that's not bad. I've done that in the past. It's a very good deal on some excellent wine. And that kind of links into social events in state by state. And again, obviously, that's been suppressed quite a bit by the COVID, but that's life, right? This is also a nice place for professional networking. And so hopefully you've been taking advantage of that. And lastly, we do quite a bit of research funding and travel scholarships for students in relation to geophysics. And for instance, here in WA, we're finalizing some student awards for some lucky students here locally. And then lastly, again, we do offer, this is kind of unique, I think, to most of these kind of societies. We actually offer free membership for students and half price for retirees. So if you do have some students that might be interested in geophysics or geology, and they don't necessarily have to be in that department, invite them to join, to apply to join, because then they everything opens up for them just like they open up for you. And I was talking about the AGC, still going, ready to go on. That's next September in Brisbane, which should be pretty neat. The abstract submission deadline has been extended now till the 7th of December. That might go a little bit farther. That should be a pretty interesting conference. And you can see that it's not just, it used to be just ASEG, but now you can see that it's shared with PISA and AIG. So that gives us a more complete set of discussions than what we had previously just from us. Pretty fun thing to attend. And then in terms of how we do keep in touch here in ASEGs, of course, any member is going to be getting our monthly email newsletters. And we have our own website. We are on Facebook, on Twitter, and LinkedIn. And then one of the neat things is we have most of our webinars and a lot of the technical talks that have been in the past are actually out on YouTube on ASEG's own website, and anyone can access those for free. So that's some way that you can go back in and review some of the talks and pick things out that maybe you missed before, or even look at a talk that you missed completely. So with that, I'm almost through. I'm ready to shut up and let Rich talk. But let me introduce him first. He's from Shearwater GeoServices. His talk is on pre-stack depth imaging. And Rich is the depth imaging manager from Shearwater GeoServices. And my screen just went blank here. Let's get closer. So let's just see what happened here. And we'll do a read along as soon as I get down to there. And he is, there we go. So he graduated from the University of Leeds, UK, and Queen's University, Canada, with a master's in geophysics. He spent his early career as a geophysicist at Veritas DGC, various roles in the depth imaging teams of both London and Calgary offices. And he moved through the various incarnations of CGG Veritas and CGG. He then went to work consulting with Monarch Geophysical Services on a range of marine and land and acquisition and processing projects before moving back to the front line with Dolphin Geophysical in 2013, which then morphed to Shearwater GeoServices. Rich has helped build Shearwater's depth imaging capabilities from scratch, which is pretty cool, with Shearwater now offering a wide range of inversion and imaging services behind its vessels and to the open proprietary market. And I do know, of course, that Shearwater has an office here in Perth. So with that, I will stop sharing and switch over to Rich.
Thanks, Todd. Thanks very much. Can you hear me okay?
I certainly can.
Good, and my presentation should be up, so if you can see that as well,
that's good. Perfect. So I'll mute myself and you continue on.
Lovely. Thanks very much. Good afternoon, everyone. It's a pleasure to be speaking with you today. I'm hoping the latency won't be too bad. I'm calling in from the UK, so if it rears its head at times, I do apologise. Otherwise, it's really good to have the opportunity to present to you today. So I'm hoping to present a case study, just giving you a small flavour of Shearwater and the types of projects our P&I, our processing and imaging group, get involved in. I'm based here in our London office, based in Tunbridge Wells in the southeast of England, although currently working from home like the vast majority of the UK this month. So my daily gripes right now are, is my heating on okay, and will my children crash my calls? I hope neither of those happen today. Anyway, let's make a start. So first of all, I'm going to take advantage of the captive audience and quickly present Shearwater today. So this is our company today. As a lot of you know, we have the leading acquisition technology in the industry. So we have Isometrics, which is the leading multi-component streamer, Q-Marine, which has 20 years of leadership in marine acquisition, and QCbed, which is the established leader for reservoir OBS. We also have the largest fleet which is both flexible and diverse, with 11 high-end streamer vessels, 3 OBS multi-purpose vessels, and 2 dedicated source vessels. We have active R&D centres in Oslo, London, and Houston, which work on both acquisition and processing technology. And our software processing and imaging group, or SPI for short, is headquartered here in the UK, and it manages a variety of projects from offshore, onshore, global pop-up centres, supporting other centres like our Perth office, and consultancy offerings, all in conjunction with our software, which is Reveal, which I'm sure many of you are aware of and may use. Geographically, this is where we're located. Most importantly, I guess the key point to highlight today is our presence in Australia in regards to software processing and imaging. We've had a local sales presence for a number of years, but we've now moved ahead in 2020 under my colleague Vincent Ganivet, who I'm sure a lot of you know. So it's his leadership, and we now have a local processing and imaging centre in a fixed office, which is just about to open. So we're very excited to be able to offer our services locally and finally in Perth now, and we hope that this local presence will open up opportunities to our clients to access our technology in the Perth market. My main objective today is just to give you a flavour of Shearwater and its processing and imaging capabilities, which isn't an easy task in a half-an-hour slot. But one way we have found it useful to engage is to present case studies to our clients, and this just gives a quick snapshot of our capabilities, our technology, our project management styles to our clients without going into too much detail. So this year we've had the fortune to present a number of case studies to our clients, a few of which I'm highlighting here. Each has its own strengths and messages, from highlighting our ability to offer onboard fast-track depth migration, to adding value to legacy seismic in the west of Shetlands, or using modern broadband and shallow water demultiple. But the one I'm going to talk about today is obviously listed last in this, which is a project recently completed in the Potiguar Basin of northern Brazil, as I think this highlights best a number of key Shearwater strengths. So let's swiftly move on to the main technical focus of the webinar today. This presentation is based upon one I presented at this year's virtual SEG, and I'm happy to present it on behalf of Shearwater and our co-authors at TGS, Shell and Windshore Dea. And the presentation focuses on the challenges and solutions to exploration scale volcanic geobody model building. So we're going to focus on two main aspects in this webinar. The first is the challenge associated with working exploration scale seismic. And by exploration scale, my definition here is a survey that exceeds 10,000 square kilometers. So these are large surveys. And it's sometimes felt that imaging such large data sets will result in a compromised outcome, whether this is having to accept a reduced quality image within an acceptable turnaround, or you have to accept an extended turnaround to achieve the desired quality. And this project aimed to try and find that balance, setting an achievable turnaround while delivering several increasing quality volumes from the processing sequence. The second aspect we're going to talk about is regarding depth imaging and model building in the presence of high velocity volcanic geobodies. And by their nature, the geobodies have a varying thickness, velocity fill and extent, and they require a detailed interpretation to be represented accurately in the model. So we're going to try and tie the two together to present our iterative methodology for this exploration scale survey. It was acquired in 2019 in the Potiguar Basin, and it totaled 10,500 square kilometers. So the inclusion of the volcanic geobodies in the model building sequence adopted a iterative manual and automated workflow, and alongside this we sequentially refined the geobodies rather than pursuing a single interpretive step. So this allowed more stages to be run in parallel, and again this was important because we expected to spend a significant amount of time on the interpretation, so we wanted to distribute that time over as long as possible, over many stages, so there's lots of things running in parallel at the same time. We also expected the interpretation to deviate significantly from the previous 2D, so expected our models to be fundamentally refined with the arrival of a fully 3D dataset. And we expected to use our other technology within our toolbox, such as reflection tomography, to overprint the geobodies to address the variable velocity fill or capture shorter wavelength bodies that were non-interpreted. So let's make a start with an overview of the tectonics and the geological setting in the Potiguar Basin. Perhaps it's one of the less known basins in terms of Brazil. I guess we talk about Santos and Campos quite a lot, but the Potiguar Basin in northern Brazil is also very prolific. So it actually includes the largest oil producing region in Equatorial Brazil. And the production is generally from the syn-rift to transitional successions. And the Pitu well in the deep water offshore part of the basin found oil, gas and condensate at depths of about 4.5 kilometers in the Upper Aptian sands of the Alagamar and Pescada Formations. So the basin began to form in the early Cretaceous due to the extensional stresses associated with the separation of South America and Africa. And the basin is heavily faulted, consisting of basement highs and lows. Related to this, we observe the Cenozoic magmatism and uplift in two main orientations. There's a north-south trending Macau-Queimadas lineament, and there's also an east-west trending Fernando de Noronha lineament as well. And the dating of the volcanic samples associated with this are of the order of 50 to 70 million years in age. So the two phases here are referred to as the Macau and the Fernando flows, although there are other localized volcanic sills also evident in the section. So starting off with the Macau, on and near shore, the Macau flows are related to continental volcanic activity, and they're represented by subaerial braided lava flows. The deposits are observed in lobe-like geometries from distribution channels, and with some evidence that parts of the flow are highly eroded. So the modern day analogues would be Hawaii or Iceland, for example. The wells that we do have indicate that the thickness of these flows varies from 300 to 1500 meters, and the velocity fill is typically 4,000 to 5,000 meters per second. These are bounded by the background sedimentary velocities of around 3,000 meters per second. So there's a significant contrast going on here. Offshore and into deeper water, the flows are thought to thin and pinch, potentially degrading from more sheet flows into pillow and debris flows. But unfortunately, no actual wells sit in the current 3D extent, so this is why it's an exploration 3D. So any of the conclusions and the extrapolations we're drawing from the wells to the south in the shallower water were treated with a fair degree of caution. Alongside the Macau, we have the Fernando flows. So the modern day analog here would be the Hawaii island chain. So the Fernando flows are related to hotspot volcanism and are represented in the seismic by a large geobody progressing from a seamount located at the northern survey margin towards the south. So in the context of the Potiguar survey, the Macau and the Fernando flows coalesce in the center into a large tabular body, resulting in a significant degradation of the subsurface image. So this is shown in this illustration, and if I just turn on my laser pointer for a second, here's the location of the Potiguar survey, and you can see we have the Fernando to the north and the Macau to the south, and in this side slice view we can see the Macau again coming from the south and the Fernando coming from the north. So the Potiguar survey sits right where these two flows meet, so it's a particularly challenging area to work. So let's review in a bit more detail the specifications of the seismic data that was acquired. So this is the Potiguar 3D survey. So firstly, we're located in the northern tip of Brazil, around 120 nautical miles east of Fortaleza. where much of the acquisition mobilization was carried out. The survey totals around 10,500 square kilometers, full fold. And I've highlighted here on the right panel the approximate location of the Pitu well in the neighboring block 2, so just sitting to the west of the western Potiguar 3D boundary. The survey was acquired in the first half of 2019 using a 12 by 8 by 100 meter streamer config, 15-second record length and 25 meter dual source. So this gives a 12.5 25 meter processing bin and a nominal fold of 80. The water bottom of the survey was a shelf setting, but cut by incised channels at the southern boundary. Here's a view looking south from the deep water towards the shelf. And if we zoom into this highlighted box that I've popped out here, you can see that the canyons and rugosity associated with the water bottom on the shelf section of the survey were very complex. So this presents clear challenges for both the processing and imaging stages of the project. I'm not going to specifically go into that today, but it's worth recognizing that, you know, these kind of issues require fully 3D solutions in regards to 3D SRME, and as well as the tomography and imaging algorithm itself. So 6 main deliverables were set. So this is obviously a project that we ran for TGS. So TGS very keen to get volumes to the market, understandably. This is a licensing round. So they're very keen to have a staggered set of continuously improved volumes through the life cycle of the processing and imaging project. So this ranged from a very fast track, or VFT, post-stat time migration, and this went all the way up through time migration depth imaging to deliver a final RTM volume. And the project management was key associated with this. So we're running multiple phases of work in parallel and testing alongside the acquisition as well. And this allowed us to get ahead, and this so that when the very fast track volume was delivered, it was delivered within 1 month of firing the last shot, and that was including shipping data from the vessel as well. So we're generally focusing on the delivery of a product E, let's say today, which is the full integrity pre-stat depth, including full model building, and this is what involved the volcanic geobody modeling. But it is important to place the effort here within the greater context of the project and the management that we require to run so many stages here in parallel. So the data prepared for model building consisted of a fast track pre-processed sequence for early iterations, which was then switched over to a full integrity dataset once available for the latter iterations. The full integrity pre-processed data utilized a modern broadband pre-processing sequence consisting of swell and cable noise attenuation, DSIG and debubble using near field hydrophone data, full broadband deghosting at source and receiver, and then followed by demultiple using a combination of 3D SRME, diffract demultiple attenuation and radon demultiple. So all this data was obviously sorted to common offset, regularized and interpolated for imaging, and then subsequently refined if we needed to target any residual noise in the common offset or CMP domain. The fast track pre-processed data was used for the imaging of the Kirchhoff post-stat time and the pre-stat time and the pre-stat depth migrated volumes. So the first 3 of our main deliverables. For the fast track model building, we adopted 2 iterations of reflection tomography. They're running a global mode, so we're updating from seabed down to 10 kilometers without explicit modeling of the volcanic geobodies. And then this was followed by a preliminary interpretation of the geobodies to be fed into the full model building sequence. The full integrity model building, this used a model building using 6 iterations of hybrid tomography. So this time the tomography has now been run in a layer stripped or overlapped kind of cascading mode from seabed down to a maximum depth of 15 kilometers. And the full geobody modeling was incorporated within this sequence from iteration 3 onwards. So that it was running in parallel through iteration 4 and iteration 5. So here's a quick example just to show some seismic. So this is an example from the first 2 of the 3 fast track volumes. So this is the first volume that the client saw. So this is the early out or very fast track post-stack time. So this is the volume that I mentioned that we delivered a month after the last shot. So a great volume for early interpretation, quick screening of prospects, quick picking of horizons. And this is not an inconsiderable size. So the scale of the section that I'm showing here is approximately 50 kilometers wide by 3 seconds. West is on the left, east is on the right. And if I move to this one, this is followed obviously in quick succession by the fast track pre-stat time and the fast track pre-stat depth. So the latter of which I'm showing here. So this is shown stretched back to time to allow us to make an easy comparison in the same domain. And hopefully the difference is clear if I do a quick toggle, and I hope this comes across okay, given the distance that I'm presenting from today. I'll do that a few times. But anyway, we see a good improvement in bandwidth, in signal to noise and imaging throughout the comparison. And again, this was considered an important volume for interpretation as an early look at the geobodies. So now let's have a quick look at the full integrity model building sequence, including the geobody modeling. So we often commence many of our projects at Shearwater with a specific stage, a model building strategy stage, and the intention of that stage is to really have a look at the data in a bit more detail before we embark and launch straight into running tomography or FWI or Q modeling or anything we want to do. And it's important to have that stage to make sure we understand the problems, that we demonstrate to our clients that we understand those problems, and for us to formulate a plan of how best to use the available time and the iterations that we have in hand. So we often commence that with something like a gamma screening stage. So gamma is the measure of the RMS move out error, which lends itself very nicely to volumetric color washes like this. So the gamma screening was carried out during the fast track model building, and it indicated a distinct gamma contrast coinciding with the volcanics top and base. So in this image, in the images I'm showing here, the color map shows anything in a blue color, which highlights that the common image gathers require a faster velocity for flattening. So the top panel is an east-west section of 130 kilometers through the survey, whereas the bottom panel is showing a 3 kilometer constant depth slice through the full survey area. So we can see a clear correlation in the east-west section of the volcanic structure with the gamma, and the depth section below highlights nicely the lobes of the Macau coming through in the south, annotated here. For the volcanics, a top and base were firstly gridded from the existing regional 2D PSDM data. These surfaces were tied to the Pitu well in the west, through to the neighboring basin, the Shearwater Basin, to give a regional picture of expected thickness and complexity. And then following this 2D gridding, we then embarked upon an initial 3D interpretation using the fast track pre-stat depth volume. So these surfaces were initially used for tomography masking in iterations 1 and 2 to avoid velocity artifacts from the geobodies leaking into the shallow sedimentary updates. And then following this, we then embarked, obviously we have 2 passes of the reflection tomography, the full interpretation of the top and base volcanics, and this was using both a sedimentary flood and a volcanic flood volume. So the upper panel I'm showing on this slide highlights the sedimentary flood image. So we included an initial volcanic flood using a constant velocity of 3,600 meters per second. This was set as a constant value, initially derived as an average from shallow wells to the south, which indicated 4,000 to 5,000 meters per second, but we then modified it based upon the flood scans and evaluating the CIG flattening across the survey. And we believe the velocity that we ended up here was slightly lower than we expected from the wells, and we believe that's probably related to the partially eroded nature of these flows. So this then allowed a base volcanic to be picked with the body sealed and the original sedimentary velocities below the geobodies preserved. So the lower panel here highlights the image after the geobody insertion. The red and pink horizons show the top and base horizons of the volcanics, and I think you can see quite clearly we observe a good improvement in the stack continuity actually within and below the volcanics. And if I then show another slide with the resulting model, you can clearly see the framework of the velocities as they're starting to build up even at this kind of mid-project kind of stage. Following this initial geobody insertion, a further wave of refinements was then carried out to the top and the base to address interpretation, footprint, any outliers, to test alternative thickness scenarios. And this is a nice example of this stage of the project. So the upper panel here highlights an arid area after the first pass of interpretation. And you can quite clearly see there's a little bit of a wobble in the depthing in these pre-volcanic events. It's difficult often to see because the section is, the syn-rift is nicely faulted, so it's often quite difficult to see deeper in the section, but certainly in the vicinity, the couple of kilometers below the volcanics, there's a clear correlation between the edges of the volcanics pinching out and a resulting wobble in depthing. So this also correlated with a pocket of non-flatness in the associated gathers in the lower panel. So a new interpretation of selected areas, selected lobes like this was carried out and paired with an overprint using reflection tomography as part of iteration 4, because we felt there was sufficient reflectivity in the volcanics themselves to justify using reflection tomography to capture this residual move out. So if I toggle to the next slide, so this is after this phase of refinement. I think you can see, and again, I'll toggle, apologies if the latency is not great, but I think again, you can see the improvement in depthing in the arid area, much more believable structures now in that area, and the reduction in the move out area within and below the volcanics as well. So after these first two stages of macro volcanic geobody model building, we then went into a more automated stage. And this was really on the basis of trying to implement a kind of global hunt to carry out, to analyze the image for any shorter scale depthing distortions, which aligned with the edges of the geobodies or excessive thicknesses of the geobodies. And so we're attributing residual and propagating depthing with an over or underestimation of volcanic thickness or velocity fill. So in order to do this, we created spatial derivative maps of the top and base and thickness of the geobodies. And these were examined in inline and crossline directions to look for lineations that may relate to remnant interpretation artifacts. We also had to change our approach here in terms of how we approach the residual depthing using a volumetric QC. In a lot of situations where there may be a short scale velocity anomaly, one route of evidence could be to use a horizon picked below those anomalies and look for correlation in the depthing of that horizon with the spatial extent of the anomalies. So shallow quaternary channels are often a nice example kind of quoted of this, but this wasn't really possible here because, as we've already seen, the syn-rift, the section below the volcanics, is incredibly faulted and distorted already. So actually there wasn't possible to pick a single horizon over 10,000 square that could be continuous to really try and correlate with that with the volcanics. So we needed to go on a different direction and use an alternative metric to kind of capture those distortions. So the route we went down was to actually do this volumetrically rather than horizon based. So we actually went down the route of using structural dip volumes to calculate those both before and after the insertion of the volcanics. These were differenced and extracted at regular depth intervals in the pre-volcanics. And then we correlated these extractions, these depth slices of the differences in the dip with the geobody depth and thickness values. And I've got a couple of examples of that now. So And this attribute-based QC was really just to highlight areas that we felt would benefit from further modifications to the geobodies themselves. So here's an example. So this is a common inline through part of the geobodies. Geobodies are sitting at this kind of level up through here. So this has got the crossline dip attributes overlain as a color wash on top of the seismic. So this is using a white centered blue-red color map to highlight the dip. The top panel is the seismic and dip before insertion of the geobodies, so effectively the sedimentary flood. And the bottom panel is after volcanic geobody insertion. So we're really looking for examples such as this, which appear to highlight a propagating depthing instability related to the volcanics, which is leading to some large dip values in that kind of pre-volcanic interval. And this can equally be viewed on in-depth slices. So the top panel shows the geobody thickness in meters. We observe the lobes of the Macau and the Fernando, along with various interpretation artifacts, little lineations that seem to align in north, south, or east, west, and sudden changes in thickness, which may or may not be expected. The bottom panel highlights a spatial derivative of this thickness. So this is using a Sobel filter. This is run in the inline or east-west direction. So the edges present in the thickness map in this orientation are very nicely and very clearly visible in this spatial derivative map. And if we now replace the bottom panel with the extracted dip difference between the sedimentary and the volcanic dips, again taken in the same inline direction, extracted in this case at in the pre-volcanics at about 4.5 kilometers, we observe some correlation. So we've overlaid a polygon here to highlight the edges of the geobodies. And what we're looking for here is dip difference anomalies that align with the volcanic thickness that propagate over a number of extraction depths in the pre-volcanic interval. So if I toggle back to the spatial derivatives of the thickness attribute map to highlight this, I think you can hopefully see that where we may see some thickness variations, they may also correlate with propagating dip differences in the section. So these are kind of areas that we could then go in and investigate and see if there's any case for any further modifications. So this led us down the route towards finalizing the project. So let's conclude why we are going to such efforts to make sure our geobody modeling is as accurate as it can be. So for pre-stat depth, we require not only an improved image over the pre-stat time, but stability and depthing. And the insertion of geobodies has the potential to improve the image, but destabilize the depthing if we get it wrong. So we started off with a fast track depth image as per this example. So this is in this case is a north-south, a cross line through the survey that sits below the Fernando flow. So hopefully you can see part of the flow sitting up in this section here. We then moved to an improved pre-stat time image based upon the full integrity pre-processing. So if I toggle back and forth between the fast track pre-stat depth and the full integrity pre-stat time, we can see the benefits of the revised pre-processing sequence in isolation. And lastly, we moved to the full integrity pre-stat depth image using the finalized geobody model. We note a far improved image and event continuity in the pre-volcanics. So again, if I toggle back to the pre-stack time, just do that a few times, so hopefully allow your eye to tune into where the differences are. We can see the improvement. Or if I toggle further back to the fast track pre-stat depth, again, it puts into perspective quite how far we have traveled. And this is the value of the sequence that we've done here, which is to provide a series of volumes that are showing continuous improvement over each other, such that when the project concludes, we end up with the optimum image. But the client has also been able to work these other data sets in the meantime. So their plans for the prospects and the leads hasn't been interrupted by the exploration scale of the project. So this concludes, I guess, my slides today for this webinar. Just a final few comments to add. I guess we note, first of all, that the interpretation of the geobodies for the exploration scale surveys such as Potiguar does pose challenges for turnaround. Modern digitalization, cloud resources is one part of the solution, there's no doubt, but there's also a part of this which is in regards to project management and structuring the project to ensure that as many stages that can be run in parallel are run in parallel. So the capturing of the geobodies here in the model was a good example of that. So incrementally updating those across the iterations, we address these time-intensive elements in parallel to the tomography without compromising on the delivery schedule or the quality. I've shown an example where we've used structural insertion of the bodies associated with tomography to overprint the variable fill, and we've utilized global QC maps adjusted for addressing this volumetrically rather than horizon-based. So using these thickness derivatives and these dip difference extractions to identify areas for further corrective actions to the interpretation. And lastly, it's worth me noting that further phases of improvement are possible for the data, either by localizing the VMB into smaller areas or incorporating other data derived or inversion techniques such as FWI to define the geobodies, but those items are for another talk. Yeah, just before I conclude and pass back to Todd, I just should like to thank my fellow co-authors from TGS and Shearwater, Shell and Windshore Dea, and TGS for permission to present the Potiguar 3D examples. So that's me done. Thanks very much for taking the time out of your late afternoon to dial into the webinar. Hopefully there's a little bit of time for any questions. However, if myself or Vincent can be of any assistance, we'd both be very happy to continue this conversation. So I've put our email addresses up on the screen as a last slide if anybody wants to make a note of those. But otherwise, thanks very much. Thank you. And yeah, back to you, Todd.
Well, thanks for a great talk. Quite enjoyed it. We do have some time for questions. Let's see. We've got another thanks from Danny Burns. Thanks for the informative presentation, Rich.
Thank you.
Let's see. Now we've got one question. It says, thanks for the presentation. Did you consider the effects of seismic anisotropy on move out and migration? I think using anisotropy aware algorithms migration will enhance these images by a stunning level. And I did notice you popped up anisotropy early on. So maybe you want to discuss what you had found.
Yeah, absolutely. It's always a tricky one, anisotropy, when there aren't any wells within the internals of the survey area. As I talked about, there's the Pitu well to the west. There's a few wells to the south. There's a regional 2D network of lines in this area that TGS have as well. So the problem we really had is that the 2D lines that are available don't perfectly coincide with these wells. So you're even though there's some value in having some well data there where you can hopefully try and establish the velocity versus delta impact of anisotropy, the 2D wells just weren't the 2D lines weren't close enough to the wells to really bring that, to guide that in, to drive that and extrapolate the observations from the wells into the 3D. But the route we went down is to look at it from more of a regional sense. If we couldn't go down the route of specifically tying individual wells into the 3D, then we looked at it more of a regional sense. So looked at the neighboring Sierra Basin, looked at Potiguar, looked at northern Brazil based upon TGS's experience and work in that area in their 2D surveys. And that led us down a route of implying a regional amount of delta and a relationship with epsilon as well. So anisotropy was included, a TTI axis as well. So it's we felt that it was the delta to epsilon, certainly in regards to the far offset kind of behavior, was was helping. There's no doubt about that, but it's uncalibrated as such within the survey. So it's one of those areas which, by its nature being an exploration 3D, you expect it probably will undergo revision over the subsequent years as licenses and commitments in those licenses are followed through to drill certain wells, which will then provide local evidence of exactly what the relationship between velocity and anisotropy is. But yeah, in short, we went down this kind of regional anisotropy route to introduce anisotropy.
Okay, thanks a lot. Yep, that's kind of what you're stuck with, I guess, when it is. It's interesting to have a 10,000 square kilometer area that has no wells, but such is life. Out of curiosity, what was the, or if you can remember, what were the largest delta values that you did incorporate into, and what?
I think we were 4 or 5% at the top end, so we're not particularly strong. The relationship I think was around 2 to 1 with epsilon, so we're not looking at hugely strong, and that was a function that we kind of hung from very smooth version of the water bottom, so it kind of draped over the structures. We did set the volcanics to be isotropic. That was felt to be important based upon other work again that TGS had done on some 2D work in the data. But these aren't strong values, but they still have given the thicknesses and the sequences we've got, it did still accumulate to deliver some nice significant improvements at the far offsets. But yeah, it's always a judge, isn't it, Todd, on these kind of projects in terms of velocity and anisotropy. It's going with what you're comfortable with when you haven't got any wells available to actually calibrate.
Yeah, exactly. So, okay, well, pretty neat. Another question coming up. I said, thanks for an interesting talk. This person was fortunate enough to do some regional gravity modeling over the Potiguar Basin this year and produced a 3D density model over the basin with comparisons between, I mean, that could be quite useful, between a laterally varying density model and your velocity modeling, help calibrate any corrections due to intrusions in volcanics. Definitely. So, well, go ahead and I'll let you go and discuss.
Yeah, absolutely. I think those are the interesting projects, aren't they, where you're working basins that may be new to you, depending on your experience. And I think certainly feeding in any sort of external information adds value to projects, whether it's wells or gravity anomalies that you can try and correlate to deeper structural picks. There's no doubt the volcanics do sit there as anomalies and may have helped. There's no denying that. So yeah, interesting observation. So I guess we always have a kind of a slight scale problem with gravity anomalies. Sometimes we get very focused on picking the edges of our anomalies as accurate as possible. And as the example showed, if you get it wrong in this kind of area, it may not always be immediately obvious when you're working such exploration scale surveys. You pick a geobody, the top and base map, and it all looks like it pinches out quite nicely. But when you look at that pre-volcanics interval, you've got to look very carefully for depthing or structures that you don't believe are real. And that's again a challenge of working exploration scale, is that you may not fully understand. You may have some preconceptions, but you may not really fully understand what structures you're actually expecting in this area anyway. So there's a danger that by chasing pre-stack depth and trying to drive a very high detailed model using volcanics, that you perhaps over prescribe the model almost too much. That there's a will to put these bodies in, but actually sometimes it can cause too much damage. So we wanted to avoid that in this project. But yeah, something like a gravity anomaly map may have been very interesting to incorporate and correlate with the final thicknesses that we derived.
Yeah, I think it would have been pretty nice if you actually happened to have that set of maps available when you started the project.
Yeah, absolutely.
So
it's always the way, isn't it? They only pop up at the end. So
let's see. So before another question pops up, I'm kind of curious. The projects I had worked on that had volcanics had pretty strong absorption. Did you have to do any Q-based kind of absorption fixes in your final data sets?
It's certainly indications of some, possibly some absorption, whether it's absorption or scattering, but there's certainly an impact in that pre-volcanics of a loss of amplitude and a bit of a loss of frequency associated with it. But it's variable. Obviously, it's variable depending on the thickness of the geobodies in specific areas. But it appeared to be more scattering based rather than attenuated. So a Q anomaly is a route that's available to obviously the main client here, being TGS. In the future, we've made some observations about potentially incorporating that, but it's not immediately obvious that it's solely a Q anomaly issue. But it's certainly a route I'm sure they'll be factoring in the future.
Well, must not have been a first order effect, or you would have been, it would have been,
No.
I didn't see that much in your final section, so maybe.
No, it's I wouldn't say it's first order, no, absolutely. It's not. If it's one of those issues, that's why we like to do these model kind of building strategy sections to make sure the technology that we're kind of contracted or we've tendered on is appropriate once the data set arrived. And actually, it wasn't a first order effect. It wasn't something that we needed to deal with early on. We all know the dangers of not incorporating Q and how that will affect the kinematics and the subsequent building of the velocity model. But no, it wasn't first order effect, but it was certainly a second order or third order effect that probably needs to be addressed or understood a little bit more. But it could be other factors in there. It could be illumination effect. There could be many other reasons why we may see a slight dimming below the volcanics.
Pretty neat. Let's see, are there any other questions from anyone? We've got another chat in here. Seeing too many more. So maybe, well, I'm actually very impressed. Out of curiosity, what you, obviously this was a project obviously in Brazil. Whereabouts were most of the processing done? I would kind of assume maybe it could have been scattered across the globe.
Yeah, so we have a variety of projects. This one wasn't actually a Shearwater acquisition. We're well known for exploration scale projects, but this wasn't a Shearwater vessel that acquired this. So obviously the acquisition contractor was shipping data from Fortaleza. So the client was Houston based with local representatives in the UK. All the processing and imaging was done in out of our UK hub, which is how we have structured things at Shearwater. Doesn't mean that's how we've only run projects. We've run projects out of Houston. And actually, one of the other case studies I flashed up at the beginning was one we talked about quite heavily earlier this year, which was another Brazil project, which we actually ran the pre-stat depth fully on board. So we do have that capability. Our vessels have a serious amount of compute on them, so we can actually, with modern VSAT and compression, we can actually coordinate to actually put imaging staff on board, knit them in with the rotations that we have in terms of QC and navigation and other onboard QC products, and actually deliver fully alongside the acquisition. So those are really interesting projects where you have to acquire, and you're actually not only just processing alongside sail line processing alongside acquisition, you're also model building on 3D data as the swaths build up as well. So this one sounds relatively simple compared to that, but actually, it's still a large volume of data, and logistically bringing that in over a 5-month period, and then obviously processing and testing alongside, such that the moment the first shot is delivered to our processing center, we want to have testing and production running along, so that the subsequent data shipments as they come in are just catching up. And so that allows us to, like I talked about, to deliver very quickly after the final swath is sealed of the final racetrack. That allows us to then ship that data very, very quickly out to our clients. So yeah.
Great. Okay, well, let's see. Any more questions? I'll give a few more seconds for somebody to type in another question. But I don't see any more. So in that case, well, I'd say ASEG would like to thank you, Rich, for getting up bright and early or early in the UK, while the rest of us are having maybe our third cup of coffee during the day for this interlude here. Appreciate it. Very interesting talk, and good to see that you were able to get all this done in a timely manner. That's always fun. Oh, and we've got just another thank you. So we'll say until next time, Rich. We'll see you again.
Great. Thanks, Todd.
All right.
Thanks, everybody.
Thanks.
Nice to meet you all.
Hey, bye now.
Cheers.